All right, ladies and gentlemen, welcome to our very first video of design of experiments. Dun, dun, dun. All right, come on, that's pretty hilarious. So yes, this is design of experiments, and we are actually going to start with a chapter 0 review. So this is, we're not going to dive into the course yet. We're going to take things nice and slow. So we actually started, as you know, with the R review before this, but now we are going to jump into reviewing some of the actual statistics stuff. So what are we going to talk about? Well, we're going to talk about some of the basics of statistics. We're going to talk about variables, what are variables and how they play a role, some different definitions that are going to be useful throughout the course of the semester. So this is actually pretty important to make sure that we're all on the same page. I do view this as stuff that you should know coming into the class, but just in case you don't, I want to make sure we take the time to talk about it. We're going to talk about critical values and p-values, what those mean, and a reminder. Actually, a lot of students really don't know what they mean, so we're going to take the time to make sure you get up to speed. And then we're going to jump into a review of some of the basic inferential statistics. I will expect you to know these, and we're not going to take a ton of time on each one. We're just going to kind of introduce them and drop them, and at the end we'll show you how to do them in R. I think we actually already talked about how to do all these in R in the intro video, but we'll have a specific one just for these. Just to review. So we'll have the t-test, the chi-squared, and then correlation, and then we'll have a whole section on ANOVA because that's going to be the main tool we use in design of experiments. The last thing that we're going to talk about is kind of conclusions. So significant and then not significant, and compare these things to one another, figure out, okay, what do we mean when we say statistically significant? What do we mean when we say not significant? And then how this impacts our conclusions. We'll have a whole section on conclusions that we talk about. How do you write these up? How do you even talk about them in a meaningful and useful way? All right, so statistics basics. So we're going to start with this idea of variables. So variables are quantities that can change. They're just things that are allowed to change their value around in the context of a problem. Typically, we write them as things that we don't know the answer to. So let's say we want to know if the IQ of cats is different than the IQ of dogs. Well, IQ is a variable. We really don't know what the value of that variable is going to be. Now, these values can change in random ways. So random meaning it's up to some level of chance. So IQ of cats and dogs, if I just took a random sample of cats and dogs, might be due to chance, because if I took a different random sample, that IQ might be different. But another, so IQ might be easy to see as a variable in that case, but maybe the harder variable to see in comparing the IQ of cats and dogs would be the type of animal. So every animal that I get would have a variable label of cat or dog. So animal is also a variable, and that can change in the context of the problem, even though it doesn't necessarily change randomly. So there's going to be many different ways that we can distinguish between variables, but we're going to focus on two. And the reason we're going to focus on two is that these two are going to be very useful for the rest of this class. So independent versus dependent variables is super important in statistics so that we can determine which variable goes in which side of an equation. So all of the stuff that we do, or much of the stuff that we do, is comparing independent and dependent variables. So being aware of what these are and being able to feel comfortable distinguishing them is pretty important. The other one that we're going to talk about is different levels of measurement. So I'm not sure, usually this is like a Math 115, a basic statistics concept, levels of measurement. Hopefully you've seen it before, but if not, we're going to talk about it here just to make sure that we are all on the same page. And we'll talk about where levels of measurement is important as it relates to our analysis. Independent versus dependent. So independent variables are variables that don't change as a result of another variable. And this is contrasted with dependent variables that do change depending on the result of another variable. So if you think about our dogs and cats and IQ, if we say, I think cats' IQs are higher than dogs' IQs, or I think dogs' IQs are higher than cats' IQs, I think that the IQ depends on the animal. So in that particular case, I'm not saying that the animal depends on what their IQ is. I'm saying if I know the animal, then the IQ will depend on that. So in this particular case, the dependent variable would be something like IQ, and the independent variable would be something like animal or type of animal. Now, there's many other terms for independent variable and dependent variable that you'll hear. I'll alternate, honestly. I kind of use them all depending on the context, but other terms for independent variable might be things like a predictor or explanatory variable, while other terms for dependent variable might be response or observed variable. And again, depending on the context in which it's used, you'll hear these different things. Sometimes people use different things for regression than they do for ANOVA. Sometimes economists use different things than behavioral psychologists. But all of these mean at least a similar thing in terms of the types of variables that they're talking about. And there's many more terms than those two. Those are just a couple of them. So for levels of measurement really indicates how much information is contained in each of the values. So there's 4 levels of measurement, recall. We have nominal, ordinal, interval, and ratio measurement, each indicating a level of strength that's present within the data. And I say strength, that's how it's commonly termed, but when we say strength in the data, what we're really talking about is, well, how much information is contained in that data point. Typically, strength goes from least to greatest, from nominal to ratio in that order: nominal, ordinal, interval, ratio. Now, this has a direct connection with the analysis that we can run. So let's first off talk about what each are. Nominal has a differing categories. So for each variable, we have different categories that we can group the variables into. So a nominal variable might be like your favorite pizza topping. We've got pepperoni, we've got sausage, something like that. Ordinal variables have categories, but then they can also be rank ordered. So my favorite ordinal variable example is ranks in the military. So you've got a private first class, etc., etc., etc. So these are categories, but they can then be ranked. Another very common example that you'll see very often when you're doing statistical analysis of ordinal data is a Likert scale. And though you may not know it by that name, you'll know it if I describe it. It is strongly disagree, neutral, agree, strongly agree. Has 5 categories and they can be ranked. Interval data has categories, it can be ranked, but it also has equal spacing between the categories. So the difference between a private and a private first class is not the same as the difference between a 4-star general and a 5-star general. Right? And the difference between disagree and neutral isn't necessarily the same distance as the distance between agree and strongly disagree. That is to say, the change in opinion that happens from disagreeing to a concept to being neutral about a concept is not necessarily the same level of change of attitude that you must have to go from agreeing with something to strongly agreeing with something. How are they different? Well, we don't know. We don't really know one way or the other. So interval data says we do know. We do know that it has equal spacing. One great example of interval data tends to be something like the temperature, where the temperature change from 31 to 32 degrees is 1 degree different, and the temperature change from 98 to 99 degrees is 1 degree different. It doesn't really matter where you are on the scale. If I just move by one number, I can quantify that it's 1 degree different, or one underlying trait different. And again, this is not the same as Likert, where though from disagree to neutral, that is one category different, the underlying trait of agreement with the concept that changes from moving your answer to disagree to neutral is not the same movement of the underlying trait necessarily that changes from going from agree to strongly agree. And then the last category we have is ratio. So ratio has all of these things, but it also adds on to it a true zero. Now, what do I mean by true zero? Well, if we're looking at temperature, that was the interval example, and we have 5 degrees, 4 degrees, 3 degrees, 2 degrees, 1 degree, 0 degrees, well, when we consider the 0 number, we can then go to -1 degrees and -2 degrees and -3 degrees and -4 degrees and on and on and on. There are some variables, though, that you can't do this with. How much do you weigh? Well, I weigh 5 pounds, 4 pounds, 3 pounds, 2 pounds, 1 pound, 0 pounds. I can't weigh -1 pounds. Same thing with height. So weight and height are great examples of ratio data in that they have categories, they have rank order, they have equal spacing. 1 inch to 2 inches is the same difference between 98 inches to 99 inches. But they also have a true zero. That is, if we're measuring something, it can't go to a negative number, whereas an interval they can. Now, the levels of measurement are actually really important, and I think they're a bit under talked about in the field of statistics. Sometimes I won't say we forget, but I'll say that it's almost taken a little too for granted. Now, one of the cool things about the levels of measurement is that if you can identify the level of measurement of your outcome variable or the variable you're interested in, this can let you know what analysis is available to use to assess that variable. So for instance, if I have nominal, I can use only a mode to assess that variable. So nominal data is mode. Now, I'm kind of highlighting the categories level here because mode has to do with categoried data. So anything that has a dot can use a mode. So nominal can use it, ordinal can use it, interval data can use it, and ratio data can use it. I can calculate a mode for all four. Then other central tendency, median, is kind of like the rank order here. So nominal data I can't calculate a median for, but I can calculate a median for ordinal, interval, and ratio. So actually on your notes, you may write mode next to category, median next to rank order, and then the last one, mean, goes next to equal spacing. I can calculate a mean for interval and ratio data, but not for nominal or ordinal data. Now there are some other terms that we can use here that are pretty common. Categorical and continuous variables are pretty common as they describe another way to look at levels of measurement. It's not under the levels of measurement branch, but it does kind of get contained in this. When I say categorical variables, I'm typically talking about nominal data, and then sometimes ordinal data. Usually ordinal data falls under categorical. So nominal and ordinal typically we treat as categorical. Then the second term, continuous, typically is interval and ratio. So nominal ordinal typically is categorical, interval ratio typically is continuous. Now ordinal is a bit of a question mark. Sometimes it falls into the continuous, sometimes it falls into the categorical. It really depends on the context. And to be quite honest with you, where ordinal tends to fall often depends as much on convenience as it does for anything else. If we wanted to do something a little more appropriate than just conveniently deciding which group ordinal went into, we could say that if an ordinal variable has a whole ton of groups, then it would typically fall more in the continuous range. If it has a very few groups, it would fall into a categorical range. And so we would care about how many groups are in the ordinal variable. But what is few or many? Well, that kind of depends. And again, that's why this ordinal variable gets away with falling kind of in the middle, is because it really is optional, and it's why it's so often selected for convenience as continuous or categorical. But as a default, I think ordinal falling in the categorical range is not bad, and then if you have a whole ton of groups, you might have it fall in the continuous. I should note that it doesn't really matter what you choose as far as running the statistic. So statistics will run it either way if you have your data coded appropriately. The problem that happens is that the interpretation changes drastically. So how you define each of these, and I use ordinal because this is the one that we tend to jump around, but it's true for all of these. How we define these in terms of categorical and continuous, or even in terms of defining a variable as nominal, ordinal, interval, ratio, we can still run analysis if we misdefine it. However, the interpretation changes drastically. The other thing that happens is not just the interpretation changes, but the amount of information that we can then use to come up with accurate conclusions also changes. So defining a ratio variable as nominal is actually okay. We just lose a lot of this extra information that we have that nominal variables don't have. Defining nominal as ratio is actually not okay because we're assuming that we have all this information that we don't have, and so making up all this data can sometimes lead us to have some pretty bad conclusions. All right, so on to critical values and p-values. Now these concepts come from something called hypothesis testing, and this is something that I know you've talked about in Math 115 and Math 116. So recall the hypothesis testing steps. So as the first step, and sometimes these are combined, I just kind of set these out as I would typically do them, but we write the null and alternative hypothesis. We set the nominal significance level of alpha, usually 0.05. We calculate the test statistic, and then we make some kind of a decision. So again, some books, null hypothesis is step 1, alternative hypothesis is step 2. Some books, instead of just make a decision, might write, calculate the critical value and then make a decision or something like that. And then after our decision, we write the conclusion. Now, the difference where critical values and p-values get separated is in this make a decision step. So in this make a decision, this is where critical values and p-values take two different routes and are two different ways in which we can make decisions about our data. So the critical value route. Now, the critical value comes from an assumed distribution of the statistic in the null hypothesis. So we use the central limit theorem very often to assume that the statistic, often the mean in the test that you've run thus far, is distributed normally or as a t-distribution with a certain number of degrees of freedom. And all of that comes from the null hypothesis. That is a starting assumption. And all of those tables in the back of the book, those are assumed distributions under the null hypothesis. So when we compare, if you've ever drawn out the picture, you've got the curve, and then you've got your little line that you're comparing on the curve. All of that comes from a assumed distribution under the null hypothesis. So it's all coming from the null. Again, we can look up these values in the back of the book. Now, the critical value separates a critical region from the distribution from the non-critical region of the distribution. And in that separation, we say, well, if our test statistic falls in the critical region, then we reject the null hypothesis and we have statistical significance. And if it doesn't fall in the critical region, we don't reject the null hypothesis. So that tends to be how we use critical values to make decisions, is we look it up, a distribution that's specified by the null hypothesis, find a cutoff value for the critical region. This comes from our alpha level. And then we separate the critical region from the rest of the distribution and look at the test statistic and see if it falls in the critical region. And if it does, we reject. Now, the p-value also comes from the assumed distribution under the null hypothesis, but it's not calculated using alpha. So normally we would go in the table in the back of the book and look up the alpha value under the assumed distribution. But for a p-value, this is a little bit different. The p-value actually, if we looked it up in a table in the back of the book, we would look up the test statistic value, not the alpha value. So it's the probability of a value at or more extreme than the observed. So if you've got a curve and you're thinking about this and you've got your test statistic, you no longer have a critical value that specifies a critical region. You've got your curve and you've got your test statistic, and now you're looking at the area towards the edge. So if you're on the top, towards the right; if you're on the bottom, towards the left. so area to the edge, at or more extreme than what you observed in your test statistic. Now for a two-tailed p-value, we need to double that area, so at or more extreme in either direction. So if we're looking for two-tailed, on the top, it's at or more extreme the top direction, but then it's times 2 because it could be that or more extreme in the bottom direction as well. So quick visual of this before we end this video. So if we've got our distribution, under the critical value approach, we look up the critical value in the back of the book, given a probability alpha. So we walk in, alpha equals 0.05. Hey, textbook, what's the critical value? The textbook says, oh, okay, your critical value is 1.96 or something like that. And you shrug your shoulders and say, okay, hey, great. So if my statistic is lower than 1.96, then I'm in the not critical region. I don't reject. If it's above 1.96, I'm in the critical region, I reject. The p-value is completely different, so we don't even have, you can kind of erase this gold portion from your mind, we don't even have that. All we do is we have the test statistic, so we do the cutoff at the test statistic, and then we find the area that's more extreme than that test statistic, so that's this area in green, and that area is the p-value. So as you can see, as this is illustrated, it just goes towards one direction, so this is a one-tailed p-value. If we wanted a two-tailed p-value, we would also have to draw the line on the other side because it could have been at or more extreme in the other direction. So draw the line on the other side and shade it over here, which because the distributions we use are often symmetric, is just multiplying this area by 2 because we'd get the same area on the other side. So this has been our quick background in our statistics. We've talked about a little bit about the hypothesis testing, the critical values, and the p-values. And from here, actually, we can start jumping into those statistical tests and reviewing the different statistical tests.